So our speaker today is Katie Morrison from the University of Northern Colorado, and she'll be talking about predicting neural network dynamics from connectivity. Over to you.
Perfect. Thanks so much. And thanks for having me. I'm definitely excited to be able to share this work and also grateful that we were able to make this happen after a postponement from February. So I want to start with just a bit of the neuroscience motivation that's been driving the questions that we ask. And then, sorry, I got distracted that something popped up in the chat. But I will leave that to Jason to pay attention to. So in particular, I want to start with the classical hot field model that's really shaped a lot of the neuroscience perspective on, for example, fixed point attractors being representative of associative memory. And so a lot of you may be familiar with this model, but just to get us all on the same page, the idea here is we have a network of neurons, and to each neuron, we're associating a state variable, S sub I, that's just a binary variable indicating on or off, that the neuron is firing or it's silent at any given point in time. And then we also have this connection strength, Wij, that reflects the influence of neuron J's firing on neuron I. Okay. And here it's a relatively simple discrete update rule that just says, okay, to determine if neuron I will fire at time t+1, we just look at this weighted sum of its synaptic inputs, compare it to a threshold, and if the weighted inputs are above threshold, the neuron will fire, otherwise it stays silent. Okay. But what was particularly impactful about this model, right, was this famous result that Hotfield proved in the early 80s that guaranteed convergence to a fixed point in the case of a symmetric connectivity weight matrix. Okay, and we don't actually think that symmetric connectivity is biologically plausible, right? But really, this was sort of a case where theory could still be built and give us some intuition for things. And just to give you a sense of how this was proven, the idea is you can create this energy function or a Lyapunov function and prove that as the network evolves, the energy of a given state is going to decrease along trajectories. And so you're guaranteed to converge to one of these local minima of this energy landscape. Okay. One important point here is just that these are static attractors, meaning that over time, it's the same collection of neurons that will continue to stay active. And we think of that as modeling associative memory in the idea that this collection of neurons, you have learned some association between them, right? And then you can accomplish retrieval of that memory through the evolution of the network, right? In contrast, though, there are also, of course, sequential memories that we have to think about how we would store and access. And those are not something that you can get out of this hot field model where you're guaranteed convergence to these stable fixed points. So just as an example of one of these sequential memories, right, if you are trying to memorize someone's phone number, you might have it repeating over and over in your head, right? And we model that with a limit cycle of activity. So just to ground everyone in how to read these pictures, because they're going to keep coming up throughout the talk, the idea is that each neuron is going to have its own color-coded curve that represents its firing rate over time. So instead of just now it's on or it's off, we're going to track its activity with this continuous firing rate variable. And then we can associate a sequence to one of these limit cycles just based on the order of the peaks of those firing rate curves. Okay, and so these limit cycles, or more generally, we could also look at chaotic attractors or quasi-periodic attractors. Any of these kind of dynamic attractors are useful for modeling not only sequential memories or position in hippocampus, but then also for central pattern generators that govern rhythmic activities like locomotion or respiration. And so here's just one more sort of flash from neuroscience data of here is activity in neurons in a central pattern generator for lamprey locomotion and for crayfish locomotion. And again, we can see this rhythmic or sequential activity that's repeating. Okay. And so what's driving the questions that we are interested in? So in each of these cases, we're starting out with some complex network that has recurrent connections. So it's not just a feed-forward chain-like structure that's producing these different attractors. We're having multiple attractors with things firing in different orders coexisting within the network. And so we have this recurrent connectivity to start, and our goal is to be able to predict the dynamic attractors that will emerge. And there's lots of different factors that come into play with that, right? So there's numerous biological complexities of different neuron types or morphologies, different synapses, noise, all of these things. But our goal is really to hone in on the role that connectivity of the network plays specifically. Okay. And so we're going to do that in a relatively simple model that allows us to isolate the role of connectivity and is mathematically tractable enough that we can actually gain some real, build some real theory there. And our goal is going to be to develop a kind of graphical calculus so that we can really think about how do we analyze this graph and directly go from features of the graph to features of the dynamics. So the context in which we're going to do this is these combinatorial threshold linear networks, which are a special family within the commonly used and well-studied family of threshold linear networks more generally. And so the idea here is they have the firing rate variable, so again, one of these continuous variables, x sub I, associated to each neuron that's tracking the level of its activity over time, or its firing rate. And then the dynamics are given by this, so that in the absence of any external inputs or synaptic inputs, so if this bracketed term were 0, the idea is that the firing rate of a neuron would exponentially decay to 0, right, with this negative xi self-leak term. But otherwise, what we're adding on is this bracketed weighted sum of the other synaptic inputs. And this time it's plus a theta that we're thinking of as a combination of external input and a threshold term. Okay. And what this brackets plus is doing for us is it's this threshold nonlinearity here that reflects the idea that if the input to the brackets is negative, we'll just set it to 0, and otherwise it'll act as the identity function. Okay. And so this is a sort of modernized version of hot field networks in that we've moved to this continuous variable representation, but we still have, in some sense, one of the simplest dynamics that we can, right? So in particular, we have this piecewise nonlinear threshold here, which incidentally is also known as the ReLU function or rectified linear units in deep learning, if you're familiar with that. But the impressive thing is that despite the sort of seeming simplicity of these dynamics with this piecewise linear function, it's actually sufficient to get the full range of nonlinear dynamics. So these threshold linear networks can exhibit multiple stable fixed points coexisting, limit cycles, chaos and chaotic attractors, and quasi-periodic attractors. And we'll see examples of all of those in a minute. But in order to really hone in and isolate the role of connectivity specifically, we're going to look at an even simpler subfamily of these threshold linear networks that we refer to as combinatorial threshold linear networks, or CTLNs. The idea being that these are TLNs that are combinatorially parametrized by a directed graph. Okay, so the idea is exactly the same dynamics, but now we're thinking of having this graph that is going to dictate exactly what our connectivity weight matrix looks like. Okay, so we're thinking of starting with this sea of excitatory neurons in this sort of sea of inhibition or blanket of inhibition, where you have specific connections that matter between, or synapses that matter between your excitatory neurons, and then you just have this global inhibition that's acting. And so we're modeling that by just extracting those excitatory neurons and the connections between them as our graph. And then our weight matrix is given by this following prescription. So the idea is if there is an edge from J to I, then we are going to think of that as an excitatory connection plus that background inhibition. And so that's where we're getting this -1 plus epsilon idea. And then in the absence of an edge between two neurons, there's no excitatory connection. And so the only thing that's mediating their interactions is this background inhibition. And so that's where we're getting this -1 minus delta value for our connectivity strength. Okay. And so we can think of that as really this pattern of weak and strong inhibition, right? It is still within the context of we're thinking of modeling these excitatory neurons, but in one of these inhibition-dominated regimes, okay? And you can think of it as like a generalized winner-take-all kind of network. The idea really is that there is this sort of constant competition between your neurons for who is going to be active, which is part of what's going to lead to this natural emergence of sequential activity. But the key thing for us really is that if we fix these particular parameters, our epsilon, our delta, and then our external input theta, right, then really the only thing that's changing as we move from one network to another is the connectivity matrix or the connectivity graph, right? And so the idea is this really allows us to isolate the role of connectivity and probe how that alone can shape the dynamics that we see. And so as I mentioned before, the general TLNs exhibit all nonlinear dynamics, but in fact, this special family of CTLNs do as well. So here is an example network, right? And this network, just by changing initial conditions, we can access each of these different attractors. So we have a fixed point at which neurons, think, what is this? Nope, that's the other one. This is 4 and 8 are active. We have another fixed point at which additional neurons are active. I can't tell in this picture anymore. I see 8 and, oh, there we go. 1, 8, and 9, this click up here corresponds to a fixed point, and that's where all of those neurons are active. We also get a limit cycle, and you can even see a chaotic attractor emerge from this network. And then we also have here another example network.
We have a question in the chat if you want to.
Yes. Okay. How are the indicated projections defined as functions, and what is the domain? Yeah. So the idea here. Oops, let me get back. So these were randomly chosen projections. So we're just going from thinking of having this 9-dimensional state variable that is tracking all the firing rate of all 9 of these neurons at a time, right? And then we chose these 2 random axes that were random linear combinations of those 9 state variables or firing rate variables in order to get these projections. And so you don't need to worry about the particulars of the projection. They were really just intended to highlight that this one is perfectly periodic, right? And so you're getting this limit cycle just looping back on itself. And this is just tracking the activity over time. whereas this one is not perfectly periodic. And we claim that it's a chaotic attractor based on simulations, that if you start your initial condition just off by the smallest amount that MATLAB will let you, you will end up in with a different pattern of pinching in this attractor. But we can't actually prove that it's chaotic, like with a Lyapunov exponent or things like that. Okay, perfect. All right. And so here, just to give you another flavor of some of the attractor types that we can see, here's another example network. This one happens to be a tournament, but that is not important. We just wanted to highlight that you can get both one of these sort of standard limit cycles as well as one of these quasi-periodic attractors, and those can coexist in the same network, and again, within this relatively simple family of networks as well. And then just because I have otherwise only been showing you tiny network examples, I also wanted to just flash, this is a size 100 randomly generated network. So an Erdős-Rényi random graph, where we have made it a directed graph though. And then here we see that there are actually, so this first one looks like just sort of chaotic activity, although you see some echoes in here of as if it were going to this periodic attractor, or some other echoes that sort of look like this attractor activity, but it never settles into anything in this one. Here we see that after this sort of crazy transient activity, we do eventually converge to a fixed point. And here we see that we converge to two different limit cycles. So we get this variety of interesting attractors in networks across different sizes. Okay. But really, what we are excited about with these combinatorial threshold linear networks is that they are actually mathematically tractable, and we can really gain some insight into the dynamics from some simpler combinatorial descriptions of things. So I'm going to tell you about some of the sort of background work that lays the foundation for what I'm going to otherwise focus on today. I wanted to start, though, by just acknowledging the many contributors to this work. So my main collaborator in all of this for the last over 10 years is Karina Curto, who's at Penn State now, but moving to Brown in the fall. And then her former student, Caitlin Parmalee, her current student, Juliana Londonel Alvarez, who is, I believe, on the Zoom here, our former postdoc, Jesse Genison, and then Daniela, Stefania, Alice, and Nikki are all part of a women's in computational topology group that first started working on some of the questions here, and then we followed up all together with that work. And so I'll present some of our results in a bit too. All right. So I want to start, though, with just some key observations from past work, which is that there is a close relationship between those dynamic attractors that we're interested in and certain unstable fixed points of the network. Okay, so stable fixed points, of course, just give us, we converge to them. They are attractors that are these static attractors where you'll get constant activity over time. But interestingly, what we've seen is that for any of these limit cycles, we also have an associated fixed point. In this case, it's just an unstable fixed point, with the idea being that if you initialize around that fixed point, you end up with spiraling out and converging into one of these limit cycles. Here, the idea is, what's sort of surprising is these dynamics are locally linear, right? So it was a piecewise linear function here. But what we can think of is, despite the fact that locally everything is linear, it's really a patchwork of different linear systems that are covering our space. So here we're getting a hyperplane associated to each of these different rate of changes, right? So for each I can take the input to this threshold and set it equal to 0, right? And on one side of that, I would get, on the positive side, I would get a corresponding equation where I can think of just dropping those threshold brackets. And on the negative side, I can think of this as being set to 0. And so this hyperplane arrangement is really partitioning our space in such a way that these, what would otherwise be just this unstable spiral out from our fixed point, eventually leaves the chamber where that linear system applied and goes into another chamber and somehow sort of comes back around and catches the spiral out a little bit earlier than where it was before. Right? And so again, then we leave this one, the original chamber where that fixed point lives, and we spiral through another, and we end up sort of patching together a trajectory that is one of these perfect limit cycles, despite the fact that we have all of these locally linear dynamics. Proving that these things really do, these trajectories really do all patch together to give you a limit cycle is surprisingly complex. It was done recently in this SIAM dynamical systems paper, but that is not going to be the focus of this talk. We're otherwise really going to be thinking about more combinatorial descriptions of things. And so it is great that we can really just associate these limit cycles with the fixed point that's in there. And so again, you can see the same sort of behavior here.
Quick question, sorry to interrupt. So did they show that for every unstable fixed point, there is an attractor, or what did they show?
So what they showed was that in any CTLN that is cyclically symmetric, maybe they actually just did it for cycles. There's a section where they're generalizing that it could be to any cyclically symmetric, but certainly for any cycle, they went through and actually showed how you can patch together these things so that you have an associated limit cycle to this cycle graph.
Oh, cool. Thanks.
Yep. Okay, and here's just another example where again we can see here we have all of these three cycles around the outside of this graph, right? And there is an unstable fixed point associated to each of these three cycles, and we get a corresponding, in this case, chaotic attractor for each. And you can see that in this projection that really there's an unstable fixed point at the eye of these things here. Incidentally, every one of our unstable fixed points, this is a Perron-Frobenius result because we're in this inhibitory case, is actually guaranteed to have a stable direction into it that is in fact going to correspond to the largest magnitude negative eigenvalue. And so we get this stable direction in, but then we end up spiraling out, right? And again, at some point get sucked back in and spiral back out. And so that's what you're seeing here with these pinches at different points and these spiraling back out behavior. Okay, and one more just visual to help you see what's going on here. So not every unstable fixed point is actually associated to an attractor, right? We can also get what acts as like a tipping point. So you can see in this particular projection, so again, here in this graph, I have a fixed point supported on this sync node 4, and that's actually going to be a stable fixed point where just that node is active. And then we also have an unstable fixed point corresponding to this 3 cycle. And we see that we get these 2 different attractors are accessible just from different initial conditions. But we also have this unstable fixed point 1, 2, 3, 4 that really acts as a tipping point between either of those attractors. Okay, and so we are going to, from here on out, be tracking the full collection of fixed points of a network. We're going to denote that as FP of G. So the idea is we can actually just track these networks or track these fixed points by the nodes that are active at the fixed point. So that's what we're referring to as the support of the fixed point. And it turns out that it's really those minimal fixed points that are going to be the ones that have corresponding attractors from what we've seen in simulations. But we will track the whole family in order to get a better understanding of this structure. Okay, and then the other important fact, right? So we can use these fixed points as a proxy for these dynamic attractors, but moreover, we can understand the structure of this collection of fixed points in terms of graph rules, right? So we can actually see how the connectivity gives rise to these fixed points in a lot of cases. And so here I'm going to just flash a quick picture of some of the style of the rules that we have. These were first developed in this fixed points of competitive threshold linear networks paper. But then otherwise we have a more recent, nice summary overview article in the notices of the AMS that really digs into these different kind of graph rules that we've developed so far. Okay. And so the big takeaways, right, is that the relationship between connectivity and fixed points is tractable, and we can use this fixed point structure as a proxy for the dynamics. Okay, and somehow I have been talking for way longer than I intended on all of this background and really want to jump into the particularly interesting new stuff that we're going to talk about, newer stuff we'll talk about today. And this is the idea of using different types of graph covers in order to really decompose our networks and get a better handle on the fixed point structure or the predicted flow of the dynamics. Okay. And so just as a motivating example to anchor everyone with what we were trying to achieve, right, as generalizations of this, what we see in cyclic unions. So these are a special type of network that we've been studying for a while, which you can really think of as sort of a cycle, but then we've inserted component subgraphs in there, okay, in place of each of those nodes in the cycle. And then you connect these components by just sending edges forward from every node in one component to every node in the next. And so this notation here is really just saying, send this to every single node in that component. Okay. And what is particularly nice about these cyclic unions is we have this theorem that fully characterizes the fixed points of these networks in terms of the fixed points of those component subgraphs. Okay, so every fixed point of the full network is precisely a union of fixed points from those local subgraphs, and every such union is a fixed point. Okay. So here are some examples. Another really nice feature of these cyclic unions is that the dynamics really do follow that cyclic structure there. So that sort of underlying cycle backbone. And so these were the key features that we wanted to think about. How can we identify these in other networks? So can we understand when there is some type of underlying structure that's going to predict the flow of the dynamics, right? And can we understand situations in which the fixed points of the full network really are composed of fixed points of certain subnetworks glued together? Okay. And in particular, part of what motivated us to look for generalizations of this was that we had seen a lot of other very similar networks with practically identical activity that are not perfect cyclic unions. So they either have an extra edge added in or edges dropped and things like this. And yet somehow we're still getting that same kind of dynamic activity. And so this motivated us to introduce this idea of directional graphs to really reflect the flow of the activity. So the idea here is a graph is directional if we can partition the nodes into an omega and tau, such that all of the fixed points of the network are concentrated in that subset tau. Plus, we have an additional combinatorial condition that I'm not going to get into here. But the idea is when we have a partition like this and all of the fixed points are in this tau component, what we've seen is that the activity tends to flow towards those fixed points. Okay, and so you get this flow from omega to tau. And that's true even when it's not a stable fixed point that's within the tau component, right? So here we're seeing flowing from neurons 1 and 2, activity that starts there, immediately converges onto a limit cycle involving those neurons in tau. Just to give you a sense of sort of the surprising diversity of these directional graphs, it is not the same thing as just having only edges forward or being feed forward. So for example, this network down here just has forward edges, but it does not have the property that all of the fixed points are contained in this tau portion or this bottom portion, because we have fixed points supported on both 1, 2 and on 3, 4, right? But surprisingly, this network, which actually has 2 back edges from tau to omega, does have this directional structure. Okay. And so the idea is that directional decomposition really gives us a predicted flow of activity. And so whenever we can start with a graph and cover it with these directional subgraphs, right, we can think of replacing each one of those directional graphs with just an edge, a directed edge. And that's what's going to give rise to a nerve for us of this cover, okay? And so the idea of what we were aiming for is some type of nerve theorems where we can go from being able to say something about the original graph in terms of the structure of its nerve, okay? Whenever we have one of these nice covers that satisfies, we also need some nice intersection properties between those subgraphs in the same way that you can think about sort of nerves of a topological space. If you have a nice a good open cover, being able to say the structure of the nerve is the same as the structure of your original covered space. Okay. And so there are a few settings in which we can say exactly this. First, I want to just show you that that nerve really is reflecting the flow of activity. So here is an example where we have chained together some of these directional graphs. And so each one of these pairs of consecutive components corresponds to a directional graph, which gives us an edge in our nerve, right? And if we look at the activity of the network, it really does just flow through those components in the same way that you would flow through the nerve. That's just that path, and eventually stabilizes at the end. On the other hand, if we associate the bottom component nodes with those of the top so that it's a chain that wraps around, right? Then our nerve is a cycle. And here we see this limit cycle of activity flowing through it. Okay. And in fact, one of the things that we were able to prove is this nice connection between the fixed points of the original network whenever we have a nerve that is a cycle. So fixed points of that network and fixed points of the nerve. So in particular, what we can prove is that every fixed point of this original CTLN is going to project by the sort of canonical map from nodes here to the corresponding component nodes in the nerve. Every fixed point here will project to a fixed point of the nerve. In this case, the fixed points of a cycle, there's just one, and it's the full support. Okay, so what that guarantees us is that every fixed point of the original graph or network is going to have to intersect every one of these components. Okay. We can actually prove something even a little stronger than that, that not only does the support of the fixed point intersect every component, but in fact, if we look at the subgraph that we obtained from restricting to that support, and we think of sort of removing all of the directions on the edges so that we get an underlying undirected graph, we're guaranteed that there is a cycle in that graph that hits all of those components in this cyclic order. Okay. Another case where we have one of these nerve theorems that's telling us a lot is if our nerve is a DAG, so a directed acyclic graph, then again, we are guaranteed that every fixed point of the original network is going to project to a fixed point of that DAG. And in that case, again, we have graph rules that allow us to understand the fixed points of this small nerve network. And so those are going to be precisely unions of the sinks of that nerve. Okay. One nice thing is that we can also iterate these. So if we start with a rather coarse cover that really captures, though, some of this DAG structure, right? Then we know, okay, the fixed points of this full graph are going to be confined to live in the sinks of this DAG. And we can then sort of iterate and find a new directional cover where we focus in on each of those sink components and can then further predict or further narrow down what the fixed points can be, and again, predict the activity even better. Okay, the other key feature that we're gonna get to very quickly is this idea of being able to break down fixed points of the full network in terms of the fixed points of these subnetworks. And the key to being able to do that, as it turns out, is this notion of a simply embedded subgraph. Okay, so here we're saying that this subset tau is simply embedded if every node in the rest of the network treats the nodes in tau identically. So it either sends edges to everyone in tau or it sends no edges to tau. Okay, and we can think about potentially covering our network with these simply embedded covers or with these simply embedded subgraphs. And when we can do that, we get exactly the nice condition that we wanted, that any fixed point of the full graph is going to restrict to a fixed point of each of these simply embedded subgraphs that it intersects. Okay. Interestingly, this sort of guarantees us a pre-sheaf structure here, where we're thinking of having a local collection of fixed points for each of those simply embedded subgraphs. And those are our local sections in contrast to the global fixed points of the network. Okay. And we have this nice restriction structure. And when we're looking at just a pair of local fixed points from these simply embedded graphs, we can understand exactly when we can glue those together to produce a global fixed point. Okay, and so if we're in one of these conditions where we can glue it together, so for example, if our two simply embedded subgraphs overlap and the sigma I and sigma j agree on that overlap, then we're guaranteed that we can glue them together to produce a fixed point of the larger network. And so in some of these cases, that's going to then give us exactly this sheaf-like structure where we can glue these local components. And so one of the things we have been working more on lately is thinking about associating a gluing complex whenever we have one of these simply embedded covers, and being able to understand under what conditions on the cover or on the original network do all of these local fixed points actually glue together to produce fixed points of the full network. Okay. Here is just an example where that works out nicely because we have overlap between each of these simply embedded subgraphs. That means we can just sort of keep iterating through that in order to say we can keep gluing together these consecutive things. And I want to just wrap up with this idea that when we combine both a simply embedded cover or partition with a directional cover, right, that is exactly when we are getting both the nice fixed point decomposition and the same kind of dynamics as what we saw in the perfect cyclic unions. So here's just a larger example where we have the same component subgraphs, and here they're arranged in a perfect cyclic union. So you have all of the edges forward from one component to the next. Here they are much more general. We just have a directional graph between each of these, and we have the property that each of these components is simply embedded. And in that situation, you can see we really are getting similar dynamics, and we are in fact getting exactly the same collection of fixed points. So every union of these local fixed points, or every gluing of local fixed points, is giving us fixed points of the full network. Okay, and so just to wrap up, in summary, right, what we've seen is that in situations where we can cover with directional graphs, we can get a nerve where the edges of that nerve really reflect the flow of activity through that original network, right? And then in various situations, we also can get or prove that the fixed points of the nerve are going to impose some restrictions for us on the possible fixed points of the original network. So in particular, the fixed points of that original network project to fixed points of the nerve. And then as an alternative sort of cover that we can investigate, if we look at these covers with simply embedded subgraphs, then we're guaranteed that the fixed points of the full network can be decomposed as the fixed points of those simply embedded subgraphs. And under certain conditions, we can actually glue together fixed points of the local fixed points from those simply embedded subgraphs to produce global fixed points of the network. And then here's just some sample open questions. This work is still relatively new and underexplored. And so we are interested in certainly identifying more families of nerve graphs for which we can get this similar flavor of nerve theorem. We also are interested in better understanding structures of simply embedded covers that are going to guarantee this property that all of the local fixed points can glue together to give you fixed points of the full network. And then finally, all of these things so far have really been used more for theoretical insight or for engineering networks to have particular properties, but not so much for starting with a network and then actually identifying, starting from a large network and actually being able to efficiently identify a cover with directional graph or a cover with simply embedded graphs. And so algorithms to be able to do that are also of great interest. All right, I'd just like to wrap up and again, thank all of the contributors to this work and then highlight a few of the relevant papers that we've been talking about today. All right, thank you.
Great, thank you. Firstly, do people want to unmute and applaud if you can and say thanks? Please do.
Thank you.
And does anyone have any questions? You can either post in the chat or just unmute yourself and ask. So any questions?
I have a quick one if nobody is brave yet. I missed a little bit. What's the point of this FG of U, like this complex fixed points of covers?
Yep. So that's because I rushed through this part. So the idea for we're thinking of two different gluing complexes that reflect two different settings in which we have seen different types of gluing structures occur. So here, this first one is just every possible union you can get where you're taking at most one fixed point per subgraph, but you are not necessarily taking a fixed point from every subgraph. But you also need the condition that those local fixed points agree on any overlap between their defining subgraphs. And then the contrast is this one is where you don't allow yourself to ever take empty set from any of those components. So it's the same idea, but here you're requiring that you glue together a fixed point from every component, not just from some, or from every simply embedded subgraph, not just from some of them. And so in particular, the reason we were motivated to have these two different gluing complexes is that in the cyclic union and also this click union, for example, we can prove that you have to take a fixed point from every component. That same thing is true in what we call a connected union as well, where you get overlap between or all of, I'll say that a little better in a second. But in contrast, if you have a disjoint union of all of these simply embedded subgraphs, then you actually, your fixed points can just take a you don't need to glue together something from every component. You can just take from a subset of component or arbitrary unions. Did that make sense, Daniela? I feel like I was rambling a little there.
No. So you want to describe the fixed points from this fixed points of the union in some systematic way, and then you have these two systems. Okay, cool. Thanks.
Yeah.
Do we have any other questions?
So I have one. So what if you replace the ReLU with some nonlinear function? So get like nonlinear threshold function networks, or is that sort of unnecessary? Because the point is that you showed that even with this ReLU linear function, you get all the nonlinear dynamics happening.
So, I mean, it's unnecessary if your goal is to have one of the simplest networks or simplest dynamics for which you can actually get the full range of nonlinear behavior. But it certainly is worth considering, because, there's arguments in lots of directions about what the most sort of biologically plausible or biologically meaningful nonlinearity really is. So there are some people who would argue for a threshold quadratic instead of a threshold linear based on what we've seen as firing rate responses. It is not clear exactly what of this theory would go through. So one of the things that we are capitalizing on throughout this is that we can characterize each of these fixed points basically in terms of Cramer's rule determinants, because these are all locally linear systems. And so we can get this really nice description of those fixed points or sort of quantities associated to those fixed points in terms of determinants of our connectivity matrix, which makes it a lot easier to be able to relate that connectivity structure to the structure of the fixed points. And if we weren't in this nice setting where we were locally linear, we wouldn't have those same tools to be able to exploit. It is true that many of the dynamics don't drastically change if we do like slight perturbations from threshold linear, so like threshold to some small, slightly larger than 1 power, for example. Then we can see sort of similar dynamics, but we don't have the same tractability of the theory in that case. Question.
Any more questions?
I can ask another one unless there's other questions. Uh, does any like higher topology play a role? So, I mean, if you look at the like flag complexes of these networks, or the homology of the flag complex, or anything like that, or you mentioned the sheaf structure, like I don't know, some sheaf cohomology of whatever you are getting, would that play any role in this dynamics? Have you thought about it?
I have not thought about it. So this sheaf structure is, I mean, this is exactly the right question to ask. And the sheaf structure is relatively a new perspective for us on this. And so we have not explored more of the homology or cohomology of things there. I do think that, let me think about how this might come into play. So we certainly think that, you know, some aspects of the topology of the nerve are going to play out in telling us things about the original network. For example, in this case, where having this cycle or this hole in our nerve graph, right, corresponded to having this kind of structure within the fixed points of our original network. But I don't know what else we can say topologically about this. And that is a great open question. Yeah.
Okay, any more questions? What I will do then is I will stop the recording, and if anyone has any questions they might want to ask that's not recorded, we'll give them a chance. I'll stop the recording.